So this is section 3, column buckling lab. Our objectives for this lab were to investigate the behavior of columns under compressive loads, to evaluate how boundary conditions affect bending response, and how column length affects bending response, and then compare the theoretical results with the experimental ones. So we start off with the equation given right here, and this comes from Euler-Bernoulli beam theory, and it comes from summing all the moments and forces on an axial loaded beam. And then it can be simplified to this equation right here, where y is the lateral deflection. And this is just a second order homogeneous ordinary differential equation. And then you just go about solving it how you would any other, and you get an r value of positive negative square root of the load over EI times the imaginary constant. And because of that, you can say that the general solution is given by right here, where there's sines and cosines. But one of the boundary conditions is that there's no deflection at the point where the beam is pinned. And because of that, this term goes away, and then you just get y equals a times the sine of the square root of p over ei times x. Now the other boundary condition is at the other length of the beam at the end, it also equals 0. So you get this, so now the inside of the sine term has to equal 0, pi, 2 pi, etc. You just set it equal to pi for this one, and because it's the first node, and you solve and you get the p critical equals pi squared ei over L squared. Now for different loading conditions, you have different effective lengths, and for the clamped or fixed one, you have an effective length of L over 2, and you can just plug it back into the equation from the last slide, and you get a p critical of 4 pi squared ei over L squared, and that's where the C constant of 4 comes in. So now we have column properties of steel, where the steel beam that we used had a height of 0.125 inches and a base of 0.75 inches, and it's a given E constant of 30 million psi, and the I can easily be calculated by 112 BH cubed, which then we get this value, and then we get the EI value. And then we have critical stress, which is this long equation right here, and we're given radius of gyration in this equation, and radius of gyration is the square root of the moment of inertia divided by the area of the cross section. And then we also get the slenderness ratio, which is the effective length divided by the radius of gyration. So then we plugged in the our values of the bars, which are 18 inches, 21 inches, and 24 inches, and we used a clamped and a pinned setup. And you can see all the theoretical critical loads given here.
For the setup of this lab, you have to make sure it's done very properly. To begin, you have to loosen the level adjust and the loading wheel in order to unattach the beam. Then you're going to load the specimen and load the balance mass in order to lift the beam and relieve all the weight from the top of the specimen. Once the specimen is loaded, you want to make sure the entire system is level. You're going to do this by using the level adjust wheel and the loading wheel in order to make sure that the bubble gauge has the bubble in the center of the area. For the testing of the lab, you want to make sure that it is level still from your setup, and then slowly rotate the two wheels, the loading wheel in the clockwise direction and the level adjust in the counterclockwise direction at the same rate. It's important that it is at the same rate in order to keep the bubble gauge level. And by keeping the bubble gauge level, you're having a constant applied load to the column. After doing this, you're going to continue testing it, and you'll see that the beam begins to buckle. Watch the outputted graphs to see where the beam load plateaus or where the beam begins to bend too much, because sometimes your data might not be completely correct.
So the first column we tested was the clamp boundary condition and the 18-inch length. So we plotted the load versus deflection data that we gathered during the testing. And you can see where the data begins to plateau is our experimental P critical value. So then after doing the 18-inch length, we also did it for the 21-inch, and you can see how the P critical value begins to decrease as the column length increases. And then finally the 24-inch length. On the same axis, you can see the P critical value is also decreased again. So after taking all that data, due to the effective length of the column, we had to multiply all of our experimental maximum loads by 4 to get these values here. And then once we compared them to the theoretical values, we came up with the percent error, as you can see, ranged between 25 and 35%. So to evaluate our data in a different way, we also graph displacement versus displacement over load. After applying a line of best fit, the slope of that line should be our P critical value. So as you can see in this one, for the 18-inch length, our slope at 102 is the P critical value here. And then increasing the length of the columns, it'll decrease for the 21 inches. And for 24 inches, just the same way as it did the last graph. To evaluate that data, we also have to multiply those values by 4 due to the effective length. And when comparing those to the theoretical P maxes, our percent errors dramatically decreased, and they're now around 4 to 8%.
So we also tested the 3 beams, 18-inch, 21-inch, and 24-inch for the buckling load, and this time it was pinned at both ends. So what we did is we obtained the load versus the displacement data using LabVIEW, and we made the plot. And from the plot, we obtained the critical load, and the critical load corresponds to the highest point on the curve. And this was done for all 3 beams. And then once we got the experiment critical load data from the plot, we multiplied by 4 due to the effective length factor, and we got the adjusted critical load. And we also calculated the theoretical critical load, and using these, we finally calculated the error. And also we used a different approach to calculate the bulking load. And this time we used the same data, but we plotted the displacement against the displacement over load ratio, and we got the slope of the best fit line, and the slope of the best fit line corresponded to the buckling load. And again, this was done for all the 3 beams. And once we obtained the experimental critical load, we multiplied it again by 4, the effective factor length, and we also calculated the theoretical critical load. And finally, using the theoretical critical load and the adjusted critical load, we found the percentage error.
This is the critical stress versus slenderness ratio graph. The orange line represents the theoretical calculations, and the blue line represents the experimental calculations. The 6 points on the graph represent the 6 different columns we tested in this lab. There were a few places for error while completing this lab. Repeated bending of the specimens over time can cause deformation and decrease critical load from our calculated theoretical value. The linear potentiometer applies a small load at the center of the column, which may result in buckling at a lower load. And for the simply supported columns, there was human error associated with keeping the system level and applying a balanced load. Some things we learned from this experiment: increasing the column length may decrease the critical load. The clamped boundary conditions allow for a higher critical load than the simply supported. Real-life imperfections can dramatically change results from what we theoretically expected. And for recommendations for future work, it may be beneficial to test a material other than steel to see how important the material properties play in column stability.